I think we've got James Grime waiting in the wings. And James Grime is a mathematician and public speaker. And he spends a lot of time traveling and talking about the history of mathematics and codes. James is the presenter on the YouTube channel Numberphile. Hello, James.
Hello, James.
Hello, James.
All right, my ears were burning, and I thought, I better join in. Yes. So yeah, Simon, who's just been on, was showing one of my my little favorite tricks. Yeah, it's just like a little mathematical effect that I found once, and I thought, let's turn that into a card trick. And I didn't even, I kind of threw it away. I kind of showed Simon. I went, look at this. This is fun, isn't it? Simon, as you can tell, loves it. Been showing it to everyone he knows. And like Simon said, we met up a couple of years later. He said, aren't you doing anything with that trick? I go, what trick was that? I've even forgotten about it. But Simon reminded me what a good trick that is. So, hey,
amazing.
James, how are you?
Hello.
Are you all right?
I'm doing well. I hope you were doing well. I haven't seen you. Well, last time I saw you was outside of McDonald's. But
oh yes, it was. Yes. So that would have been, was it
this time last year? Yeah, annual Maths Jam.
Yeah, okay. Well, what a glamorous picture we're painting. Yes, quite. But yeah, well, am I doing well? Well, it's been a weird year. You say I travel a lot, because that's the job. I travel a lot and I give talks, but not at the moment. So it's a weird year, I must admit. Are you ready for some magic?
Whoa!
You see, that's the action. That's the action you do. That means magic. Okay, let's do it. Let's crash on. Let's do it.
Brilliant. Let's go.
I'm going to show you one of my favorite magic tricks. This is one that is really easy to do. You can pull this out at any time, and I've done it for all sorts of people. Rooms of mathematicians and everyone else. So what you need, James, you're going to be my volunteer here. You need your calculator.
I have my calculator ready.
Excellent.
Let me put on
but
the visualizer.
You won't need your visualizer. That's fine. You can hide that because I don't want to see anything. That's very important. So you've got your calculator. For other people who are going to perform this trick, people have calculators on their phones. You can do this at any time now. You just whip out your phone, do this trick. So what I'm going to ask you to do, James, you got a choice. You got a choice. I tell you what, I've got my favorite calculator, which is in my drawer here, is really old fashioned. It makes all the beeps every time you press a number. Every calculation is just accompanied by beeps. It makes me feel really mathematical. Now,
I love it. This is amazing.
So you've got yourself your calculator. So simple thing.
I have indeed.
All I'm going to ask you to do is multiply single digit numbers together until you get something big. So I'm asking you to go 2 times 3 times 7 times 8 times 9 times 1 times 2 times 3, whatever. Just mix it all up as well until, I don't know, it's over 1 million, between 1 million and 1 billion. Maybe it's 6 digits long, 7 digits long, 8 digits long, 9 digits long. I don't mind. Big number. Multiply those out. Like I said, mix it up, make it hard for me. Multiplying single digit numbers. I've got a big number. And you've got a huge number. Now, this is what I'm going to ask you to do. So you say it's a huge number. I mean, how long is it? Is it like 7 digits long? Is it 8 digits long?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
10 digits
do say if you want.
That's great. That's great. You've got a 10 digit long number, right? Massive number. This is what I'm going to ask you to do. I'm going to ask you to pick one of those digits in that number as your secret digit. All right, so that's your secret to remember. That means the other 9 digits in that number, I want you to give me the other 9 digits in any order you want. It doesn't even have to be the correct order. So you've got 9 digits to tell me in any order you want and a secret digit you're keeping to yourself. I'm going to write those digits down as we go along. It makes my life a bit easier. What are the other digits in your number?
4.
You got 4.
6.
6.
0.
0.
0.
0.
8.
8.
8.
8.
3.
3.
2.
2.
5.
And 5. Interesting. And then maybe I'll put a question mark to represent your number there, right? That's your secret number. Have you got your secret number? Is that correct? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and a secret number.
I've given you enough. I was worrying I wasn't going to give you all of them because I've given them in a random order.
I was checking we were doing this all correctly. So now you're thinking of your secret number. You need to transmit that secret number to me. Yes, transmit it over the internet.
By the power of the
hat.
hat.
Predict your secret number, what you're thinking of. So if I predict this correctly, and I'm worried about this, this is difficult. So I think, I'm not quite sure what you're thinking of actually. So I'm going to predict, still predicting. Okay, so are you concentrating? Are you sure you're concentrating? Because it feels like you're thinking of nothing. Are you thinking of nothing? Okay, I'm going to predict, and this is where it goes wrong, that you were thinking of a 9. Is it a 9?
Yes, 9.
Oh, it's a 9.
That's amazing.
Right. So, first of all, can we just confirm I got that right?
Yes, a 9. It's a 9.
Phew. Right. Now, that was a bit, I was a little worried about for there. So, we're going to explain how this works, and people can do this themselves. So, this is based on something called the rule of 9. Do you know the rule of 9, James?
I've heard of it, yes.
Maybe you do. Maybe. Okay, so the rule of 9 is the idea that multiples of 9 add up to 9. Okay, so here you go, low tech. Here, look, here are the multiples of 9, I wrote them out. So the multiples of 9 add up to 9, by which I mean the digits add up to 9. So there you go, 9, 18, 27, 36. There's your multiples of 9. Let's add up the digits. Well, 9 by itself adds up to 9. 18, add up the digits, 1 and an 8. That's a 9. 27 adds up to 9, so on. It kind of goes wrong here with my 99, adds up to 18. And then it goes right again. 108 adds up to 9, 117 adds up to 9. So what actually I want to say is multiples of 9 add up to 9 or multiples of 9. So it could be 9 or 18 or 27 or 36 and so on. Now, why is that? Quickly, I'll do a quick explanation of why that is. There's a harder explanation, but we won't go into it. When you're adding 9 to your number and going up each time, every time you add 9, well, the 10 digit goes up by 1, the unit digit goes down by 1, doesn't it? So 18 to 27, one number goes up, one number goes down. So that sum, that digit sum, doesn't change. Occasionally it goes different, like from 90 to 99, it goes up by 9. So it's jumped up a multiple of 9. So it's gone up to 18, but then it jumps down again by a 9 as well. And then you get that same idea again. That's the quick explanation, right? Adding 9 doesn't actually change the digit sum unless you go from 9 to 18 to 36 to 27, right? I was banking on your number that you've just created on your phone being a multiple of 9. Now, this is not guaranteed and it doesn't always work. So, but I was banking on it being 9 because I was banking on you at some point when you're multiplying your single digits, doing a multiply by 9 at some point. As soon as you've done multiplied by 9 once, the answer is a multiple of 9. Or maybe you hit a 3 and a 6. That would work the same. Maybe you do that a couple of times, then I've got a multiple of 9. So I was banking on this number that you gave to me being a multiple of 9. So all I was doing was adding up the digits and then seeing what digit I need to make a multiple of 9. Now, actually, let's do it. So we got a 4 plus 6 is a 10 plus an 8 is an 18 plus an 8 again, or 26. A 3 is a 29, a 31, a 36. And that's when I started to panic because it added up to 36. Now, that's the difficult bit. Because that means your question mark had two possibilities. It could have been a 0, or it could have been a 9, because that's what we want. This should add up to 36 or 45. That's what I was expecting. And you gave me a difficult one to work out. So I had to do a bit of a magician thing here, which I don't know if you spotted, and I was kind of panicking. Okay, transmit. Are you thinking of nothing? Did you notice I was doing that?
Yes.
I was judging your reaction. Because if you were thinking of 0 and I said, you're thinking of nothing, you would have gone, oh, he's done a joke. He's done a thing. And what you did instead was go, yeah, I'm really trying. I'm really concentrating. I don't know what you mean. So, right. So it's the other option. So it was a 9. So I had to do a bit of a magician thing there. However, if you had not picked a 9, let's actually put this in here. So that would have been all the digits of your number. If you had not picked a 9, let's say if you picked the 2 instead, then this would have added up to 43, I guess. That would have been easier. I go, oh, okay, it adds up to 43. Therefore, I'm expecting it to be 45. Therefore, I'm missing a 2, right? And I would have said 2. That would have been much easier. It's a lovely trick. Rule of 9, that's what I've called it. And I'll give you something else with this as well, because this is what accountants used to use in the old days, 100 years ago or more, before calculators and spreadsheets and so on. If you were an accountant and you were doing a series of calculations, you'd use the rule of 9. Now, I'll do an example, right? Let's say we're going to do a calculation, right? Easy, something easy. All right, so let's say 326, there you go, plus, right, you make something up, 523, right, plus, I'll just keep going, 130, right? And in real life, this would probably be more difficult and longer, right? And let's say I'm doing that adding up. Now you add that up in the traditional way, column by column, okay, 6 plus a 3 plus a 3, all right, it's a 12, 1 left over, all that stuff, right? 2 plus 2 plus 1 left over is 6.
6.
And then we've got a 3 and a 5 and a 1.
9.
Okay, it's a 9. So 962 is what I've got. Maybe I'm worried. Maybe I haven't done it right. How can I check if I've done it right? So this is what accountants used to do. They used to use these digit sums. So I'm going to look at the digit sum here of 326. Okay, what is the digit sum? 3 plus 2 plus 6 is 11. All right, it's 11. In fact, you can go one step further. I can reduce this down one more step. 11 would reduce to 2, 1 plus 1. So that's called the digital root. It's the smallest number when you do this. Let's do it again with the second number, 5 plus 2 plus 3. I've got that as a 10. And if I reduce it further, it's a 1. Okay. And this last one, 113, it's the 5. That's pretty much reduced. Okay. Now, if I perform the same calculation, but this time using my digital roots, let's do it. This is just adding. It could be multiplying, though. It could be subtraction. It actually all works the same. You do the same calculation with the digital roots. So it's just 2, 1, and 5. That's an 8.
Yeah.
Okay. If this is correct, the digital sum has to be 8. If it's not 8, it's not correct. So this answer that I had, 962, that's what I'm checking. I'm checking if it works. So 9 plus 6 plus 2. I got that to be 17. And 17, yep, reduces to 8, which is exactly what it should be. Now, if that had been wrong, then I know my sum was wrong. And that's how you check. So it's a little thing that they used to do in the old days. Digital sum. Great little trick. Yeah, I've done this before.
Amazing.
People may have seen this. I've done it on the internet before, so people may have seen this. I once did this some years ago with a magician, an American magician called Brian Bushwood, who's a YouTube magician on Scam School, Scam Nation. Great guy. And I contacted him on Twitter and said, let me do this trick to you online on Twitter. Did what I just did to you, you're thinking of. 2, he loved it, he was amazed. So we set it up online. We did a YouTube video with all the instructions and we got people to tweet us the numbers. And
that's fun.
And we sort of direct messaged them saying, you are thinking of 7. But the great thing about it is we automated it. We had a script. So people would tweet to us and then this automatically, they just got magicked at them. So we were just doing thousands of these. It was a great
create a nice Twitter bot with that.
It was good. It doesn't work anymore, so I'll say that. But it's one of my favorite tricks. Now, I know, and I'm just crashing on and taking over.
It's fine. Take your time. Do what you want.
Trick. Oh,
Show me maths.
I'm doing it. I'm doing it.
Good.
Great
James,
trick.
go.
Love it. I've got a second though. So we try that one. So we just bash through, try our second trick.
Let's get some more maths. Come on, let's go. Let's go. Maths time.
Well, we'll see about that. Right. This
Do I need anything for this one?
Well, I've got my props over here. So this trick involves a set of dominoes. So I'm not expecting you to have a set of dominoes, James, right? But for people at home, you can grab a set of dominoes. You can do this trick yourself. So let's do it. Actually, I'll show you my set of dominoes. What I'm going to do is switch my camera. So here is my set of dominoes. There they are. This is, a double 6-pack of dominoes. I've actually taken the doubles out there. I don't know if you can just see. There you go. There they are. Those are the doubles. I took them out, not for any reason. There's a double 2. Not for any reason. Doesn't spoil the trick. You can do it with the doubles, but it makes my life a bit easier without the doubles. So you can do this very, very easily. So you've got yourself you've got yourself your set of dominoes. Now, this is what you ask your volunteer to do. You're going to make a chain of dominoes. You know how dominoes work. You connect the numbers together, right? Make a chain, right? So that's what you're asking your volunteer to do. So you go ahead, go for it. So let's start, right? You go, okay, there's your 3 and a 2, and I can join the 3 on like this. All right. So I'm going to do this, and this.
You're a bit out of frame there, but.
Oh, okay. Let me just bring it down a little bit. So this is not amazingly entertaining, right? So I'm just going to give you something to think about while I make this chain, which is how many dominoes are there in the standard double 6-pack of dominoes? So what numbers do you get in the double 6-pack? You get zeros, which are blanks, and then you get all the other numbers, your 1, 2, 3, 4, 5, and 6. Okay, so how many dominoes would I have? I have taken out the doubles though, remember. So maybe you want to think about that as well, with or without the doubles. Now I'm going to carry on making my chain. Let's see.
Isn't there a nice triangle there with the dominoes? I think you can get nice triangles out of writing.
Well, we'll see. And one question to wonder about is, can I make a chain that uses all the dominoes? I mean, is that possible? So I'm going to carry on like this. And what are we missing now? So I need to get, am I stuck? Have I got to a stuck place? No, I've got a 4.
No, you've got 4, 1.
And a 5, a 5 and a 6, 6 and a 3. Oh, and I made a complete chain.
Hey!
A 4, sorry, a 3 and a 4 there. So there's your complete chain. But I've got these 2 ends. Now, I actually made a prediction. There it is on that piece of paper. Made a prediction before I started. I've got these 2 ends. Okay, what ends have I got left over? I've got a 2 and a 4. What was my prediction? Well, you might be able to guess. Hey, there we go. Say 42. Okay, so that was what I predicted would happen. So I don't know if you were able to complete the chain or anything, but yet I could predict what the 2 ends was going to be. So how can I do that? I'll switch back to my original camera. Okay, so how do I do that? So the idea here uses a bit of what we call graph theory. It's the idea of networks, dots and lines, networks. London Underground map is a network, that idea. So here's what I wanted to show you. You get these kind of puzzles as kids. So this is something you may have seen. And let me hold up a few networks. Here we go. There's some networks. My question is, can these networks be drawn with a single line without taking pen off paper? Right. So in one line. For example, this first one looks a bit like a fish. Can that fish be drawn with one line? Oh, yeah, actually it can. I'm going to start with the tail and I'm going to go bop, 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 bop. Yes, it can be drawn with one line. So that's what I mean by drawing one line without taking pen off paper. What about this second one? Can that be drawn with one line? If you start with the tail, you actually get stuck because that's got a horizontal line there. I've not been able to draw that. So actually some places you can't do it. If I start here on the nose of the fish though, I can draw the outline, end up back on the nose and poof, I can do the horizontal line as well. So I can do it. So some places I can't do it. Some places I can do it. Same for this little fish here with the vertical line. If I start here at the top of the vertical line, do the fish outline, draw a vertical line, you've drawn it all in one go. Brilliant. This one here, you've got the 2 lines now. Can that be done in one continuous line? I wonder. You can try, do the fish outline, but I do get stuck. Maybe if you do it in a different position, can you do it then? Think about that. I wonder, can you do it? This one here, that one is a bit of a house. This is one you do get as a puzzle as a kid. I don't know if you saw this one as a kid. It's a house. Can you draw this house without taking your pen and paper? So you do this sort of action, and yes, you can. Here's one, house without a ceiling. Can you do this? I'm going to say no. So why not? So here's the answer. When you're drawing these pictures, every time you go into a junction, every time you go into a point, you then exit the point. So you're trying to draw it and you're going in and then you go out. You enter and then you leave. So every one of these points should have an even number of lines because you go in and then you go out, in and then out. So it should have an even. Yeah. Except for the start and end point. They could be odd where you start and end because you go off, then you do your ins and outs, and then you end up somewhere else. And that could be an odd number. That's what's happened here. On this second picture, we've got 1, 2, 3 lines coming out the nose, 5 lines coming out here, just where the tail is. So those are odd, but that's your start and finish point. That's allowed. This fish down here, 3 odd points, 3 odd points, 3 odd points, 5 odd points, too many odd points. That means you can't do it because you do need an even number except for the start and finish. Okay. So that's called an Euler trail. This goes back to Leonhard Euler. Königsberg bridges is a famous problem. That's the idea. So what about my dominoes? Well, my dominoes use the numbers 0 to 6. So I'm actually going to draw that on the pad here. I'm actually doing it now, doing this live. So I'm going to draw out numbers that were on my dominoes like this. 0, 1, 2, 3, 4, 5, 6. Each domino can be a line in this little graph that I'm going to make. For example, the 0, 1 domino, the blank 1 domino, I'm going to represent it with that line. That's the 0, 1 domino. 0, 2 domino is like that. The 1, 2 domino is like that. That represents the 1, 2 domino, and so on. You do all the dominoes. This is what you get. So that's it, all complete, right? And every point connects to every other point. So that represents my set of dominoes. If I wanted to do my doubles, it would be a loop here. If I wanted to do double blank, it'd be a loop. Right, it's 0 connected to 0. That's without the doubles. So there's all my dominoes set. Every point is connected to every other point. That means every point here has 6 lines coming out of it. So every point has an even number of lines coming out of it. That means if it's an even number of lines, you can make a circuit. So you can always make a circuit, end up back where you started, either using up every edge here, every line, or using some of the lines, but ending up back where you started. That will always happen. So what happened with my trick over here? Well, actually, I lied to you. I did lie to you at one point because I said I had a complete set of dominoes here. I actually don't. I'm going to go back to my camera again. I did ask you how many dominoes are in a complete set of dominoes. Without the doubles, there should be 21. And actually, if you look there, if you count up, there's 20. I took a domino away. And which domino did I take away? It was the 4 and the 2. There it is, completing the circuit. So you end up back to where you started. So by taking that away, I knew that it would have 2 loose ends, and it would be a 4 and a 2. So I can make my prediction. It's a lovely little thing.
That's really cool. I really like that. That is amazingly cool.
It's a little fun thing. A couple of questions to think about. I know we're coming to the end of my time. A couple of things for you to think about. So, for a start, does it matter if I add in the doubles? Does it break the trick if I add in the doubles? Okay, so think about that. Add in the doubles, does it break the trick or not? Why not? Okay, or why? My second thing I wanted people to think about is this is a double 6-pack. You get them in shops, double 6-pack. I'm not impressed by double 6-packs because from my background, my granddad was a dominoes player. He was a proper dominoes player. And as a proper dominoes player, he used to play with this. This is my granddad's dominoes set. Right, this is my granddad's dominoes set. And this is a proper set. It's a double 9 set. So this goes up to 9, blank to 9. So you can see, if I can hold it up there without it all falling out, you see all the other numbers, but you see you've got a 7 there, we've got a 9 there, I think we've got an 8 over here. Okay, so it's a double 9 set. Will this trick work with my granddad's double 9 set? Okay, so that's something I'm going to leave people thinking about. How about that? I will leave it there. I've been talking straight through. So before we go, do you want to quiz me about anything?
Oh, have you got anything to plug first before I start quizzing?
Okay, things to plug. No, I've not got things to plug. I don't.
You sure, James?
I've got nothing to plug. Follow me on Twitter if you like that sort of thing. If I've got anything to plug, I'll say it there probably. I do have a Facebook. Singing Banana. Okay, Singing Banana is my YouTube channel, my actual original YouTube channel. And there is a Singing Banana Facebook page, which I use less frequently because less people are on it. But there's and also my James Grime at James Grime Twitter. So if I've got something to plug, I'll say it there. I mean, number file videos are awesome, which you'll see me regularly on.
We love Brady.
Singing Banana videos, which I'll do now and again. And currently, I'm working with an organisation called Maths World UK. Maths World UK are trying to create the UK's first national maths discovery centre, because it doesn't exist in the UK. So like a science centre where you've got things to turn and things to pull, and right, like one of those kind of discovery centres, but for maths. Now that exists in other countries. And they have it in New York, and they have it in Germany, and they have it in other countries. Spain has one, but we don't have one in the UK. We're trying to make one real physical building that will exist. Well, I'm part of that. And as part of that, I have been making videos for them in this kind of situation, kind of Zoom calls, me interviewing someone else, and asking them to do a bit of maths, just like this, what we've just done today. So that exists. So that's Maths World UK. That's a YouTube channel called Maths World UK. And we've got some videos there and more to come. And
I've been keeping up with them.
Leaning towards things to make and do is what I ideally like to do. Things to make and do at home.
That sounds amazing. One question before we run out of time.
Yep.
If you could solve any mathematical problem, what would it be?
Yeah, I'm never good at these questions, but I'll give you an answer. I do like the super permutation problem. So the super permutation is, first of all, what is a permutation like? If we had the numbers 1, 2, and 3, how many ways can I arrange the numbers 1, 2, and 3? Okay, or what are the arrangements of 1, 2, and 3? 1, 2, 3, 1, 3, 2, 2, 1, 3, that. Now, a super permutation tries to put that all in a string. Puts that all in a string, so it overlaps as well, so that these permutations overlap, so that the string is as short as possible, but contains within that string every possible permutation. Let's say 1, 2, and 3. Now, of course, the next step up is, can we do it for 4 numbers, 1, 2, 3, 4? Can we do it for 5 numbers, and so on? And what's the smallest string we can do it? Now, we have answers for 3, 4, 5, 6, I believe, but 7 we don't have an answer for, and I'm not even sure we've proven that 6 is the smallest one. So that's a nice little problem that I'm kind of interested in.
Brilliant, thank you, James. I think that's all from James and James. Oh,
the James I, the Jim I. I believe that's
James squared. So thank you, James.
See you, everyone.